Okay, so in this problem we have two blocks attached with a string. So we know we have to think of it kind of as a system of objects moving. And one of the blocks is on a rough horizontal table, which means we have friction. And the other block is hanging over the edge, right? And we're told the pulley that attaches them is frictionless and massless, and the string is also essentially massless. So it's just the two blocks that move. And so our first step in this problem is to draw a free body diagram, right? That's what part A is. So this is block M1, which is the one that's on the table. Right, so we draw our block, and we think about what forces we have. Well, the most obvious one, I think, has got to be tension, because there's a string attached to the block. So that tells us there's a tension force to the right in the direction of the string. The block also has mass, so there's a force of gravity. You can call it weight, you can do mg, whatever you want, but straight down. And since it's not falling through the table, we know there's also a normal force up, right? Normal force. And then finally, there's friction, right? If we didn't have friction, this block would be sliding to the right. So that means that friction has to point backward to the left. And since we aren't told if the whole system is at rest or if it's moving, we don't know if this is kinetic friction. That's a terrible F. We don't know if this is kinetic friction or static yet. All we know is it's friction, right? No matter what's happening, friction is going to point that way. So I'm not going to write F sub S or F sub K because I don't know which one it is yet. All right, so that's part A. Right, we're going to be using that in part B, so it's important to get that carefully right. So in part B, we have to figure out the minimum value of the coefficient of static friction, mu s, that prevents the blocks from moving. So this means that for part B, this is a static friction force, right? So for part B, we know it's static friction because it's not moving. So here, right, A equals 0. That's what not moving means, right? It's not accelerating. And so if we write the net force on block 1, right, that equals 0. So you notice here that I've written x. Why x for horizontal forces? Well, I know the block, right, when we're talking about friction, we care about horizontal forces because this is a horizontal force. So I'm only going to write the horizontal forces for now. I might need the vertical forces later, but I'll start with this. So, because that's, right, this is for block 1, that's where the static friction force appears, so I start with that. So, now we have to use our free body diagram to write the net force. Well, the tension is in the positive direction. The static friction force is in the negative direction, and that equals 0, right? They're in equilibrium. Okay? So this tells us that the tension force equals the static friction force. So if we're asked about the minimum value of mu s, that means we're going to use the relationship that Fs is less than or equal to mu s times n, but we just want the quality, right? The minimum value of mu s means that we sort of get the maximum force for it, right? So the maximum amount of static friction that we can have for a given mu s is when those two are equal. So that means we substitute here. And so now we need the normal force. Right, the normal force is in these vertical forces. So we're going to write the sum of the vertical forces equals 0. Right? It's not accelerating up or down either on block 1. So the normal force minus the force of gravity equals 0, or the normal force equals m1g. Right? So we can plug that in. And so we get, as I kind of move down diagonally here, mu s m1g. Okay, but we still don't know the tension. That's a problem. But we have a second block, right? We have block 2, and its free body diagram is pretty easy, right? Just two forces, tension up and weight down. And so if we take this block and write the net vertical force is 0, right? If block 1 is not moving, block 2 also cannot be moving. They're attached with a string. So we have the tension minus m2g, right? The weight equals 0, or the tension equals m2g, right? And these tensions must be the same because the string is massless. So now, right, I'm going to, where we have this and this being equal, I'm going to substitute this in. Right, so kind of starting a new spot, we get m2g equals mu s m1g. G's will cancel, and we're left with m2 over m1 equals mu s, and that's our final answer. Right? You notice that I just kind of carefully worked through it, starting with free body diagrams, identifying the acceleration from the description of the problem, then using my free body diagram to fill in the net forces, and just writing Newton's laws repeatedly until I got rid of all my unknowns. Right? I started off with the horizontal forces for block 1 because that had the friction force in it. Then I realized I needed the normal force, so I talked about the vertical forces of block 1. Then I realized I needed the tension, so I talked about the vertical forces on block 2. Right? So that's part B. All right, so part C, this is, we have to describe what happens after the push is complete. So I give it a push and then I'm done pushing, and we have to figure out what happens after that. Right? So since now the acceleration is an unknown, we're going to have to write the same sort of equations, but with less things being 0. So we're still going to write, right, if we care about the acceleration of block 1, that's a horizontal acceleration. But now this is not equal to 0, right, because it's moving. Our horizontal forces are still the same, mostly. Tension still pulls it to the right, and the force of friction still opposes it. But now it's moving, so it's kinetic friction, right? And we know the definition of kinetic friction, right? It's always the same thing. Okay, so we're getting there, right? Mu k is a given, but we don't know the tension or the normal force. But we can find the normal force, right? This is something we can find, similarly to what we wrote last time. Even though it's moving, block 1 is still in vertical equilibrium, right? It's not accelerating up or down. So this equation still is true. So the normal force minus Fg0, or the normal force equals m1g. That's still true. So we can take that and put it there. So T minus mu k m1g equals m1a. And so now we realize that if we want to solve for acceleration, we need the tension, right? And that's actually what part D is asking as well. So we need acceleration and we need tension. And that answers C and D, but we don't know either of that equation. So we need another equation. And once again, I'm going to go to the other block. Right, the other block, block 2, right? Again, the acceleration is not 0. It's the same as block 1. Whatever this acceleration is, this is the same, magnitude-wise. However, the direction is different, right? Negative A. Why? It's moving down, right? Block 2 goes down. Block 1 goes to the positive right direction. So we can again write the net force, tension minus Fg of block 2 equals negative m2a. So if we write tension minus m2g equals negative m2a, now we see something pretty nice in these two equations, right? We don't know tension, we don't know a, but we know everything else. We have two equations and two unknowns. So if we solve the system of equations, we're going to answer both parts C and D. Right, so if I do that, I'm going to solve for this one, T equals m2g minus m2a. I'm going to take that and put it in over here. And now it's just a lot of algebra. Right? So this will get us the acceleration because I've eliminated the tension variable. I'm going to put the acceleration, oops, this one is m2, not m1. Erase that. Okay. I'm going to put the acceleration terms all on one side. So that means moving this one over. So we have m2g minus mu k m1g equals, and I'm going to factor out the a. And so I can solve for a by just dividing by that thing in parentheses. And I will get a equals m2g minus mu k m1g all over m1 plus m2, right? And that's part C. Once you get part C, then part D is really simple. We just take this and plug it right back in. And so, well, actually I should draw that arrow a little bit better, right, to where we're plugging in, right? We're plugging in for an acceleration. We plug it in right there. And so T equals m2g minus m2, m2g minus k m1g all over m1 plus m2, right? And that, even though it's really, really, really ugly, should give you the right answer, right? So our final answers are this and then that. And you don't really need to simplify this unless you really want to, but I wouldn't advise it. There's no reason to do the extra algebra, right? You just substitute it in and then you're done, right? And so that's the entirety of this problem, right? Lots of Newton's laws, lots of free body diagrams, just carefully following the steps and remembering not to skip too many should get you the right answer.